Okay, so previously, okay, we had talked about how the new rotational quantities are related to the old linear quantities. Okay, so chapter 2, okay, first week, we had a car going down the road, velocity was to the right, okay, x was its position, all right, and then we said, okay, if you take the road and you bend the road around the circle, instead of after a couple minutes that car being so far to the right you can't see it, now that car is just rotating around. Instead of talking about the linear position x, we can talk about an angular position theta. Okay, and if the car moves down the road, there's a linear displacement delta x. Well, as the car, let's say, goes around a circle, or if a wheel spins in a circle, then we can talk about an angular displacement delta theta. And just like the position can change, okay, so when the position changes, the car has a velocity given by time rate of change of position. We showed that the angular velocity omega is given by the time rate of change of angular position. So there's that perfect mapping. So between the linear world x to the rotational world theta, so from position to angular position, and from velocity, okay, so velocity gets mapped to its rotational counterpart, angular velocity. And then we'll make the analogy that as the car speeds up here, and the foot is on the gas pedal, when the velocity increases, the car accelerates. So if I have a spinning object here, if the spin rate changes, so if omega changes, then the car's angular velocity can change, and we say the car would have an angular acceleration alpha. So we use a for acceleration, alpha for angular acceleration. So the angular acceleration, okay, it looks just like a. So instead of a being time rate of change of velocity, now angular acceleration is time rate of change of angular velocity. And we'll see in a little bit that we can treat the angular acceleration as a vector. So in a little bit we'll write it like that, okay, because a is a vector, right? Acceleration is a vector, so we can treat angular acceleration as a vector. But right now, let's just look at the magnitude of it. Okay, let's look at the units as well. Okay, so the units of the angular acceleration alpha is you have units of omega on the top, radians per second, and you have units of time on the bottom. Okay, so radians per second divided by second gives you radians per second squared, which reminds you of in chapter 2, acceleration was meters per second squared. Okay, so that kind of matches up. That makes sense. All right, and then back in chapter 2, we had cars that sped up and slowed down at a constant rate, much like if you drop something or threw something up being in free fall, it would speed up or slow down at a constant rate. So we said that if the acceleration was constant, then we don't have to talk about an instantaneous value because it's the same all the time. So if the angular acceleration is constant, so that means a wheel is spinning up, or the spin rate is changing at a constant rate, or let's say like your tire, if you're slamming on the brakes and your tire rotation rate of the tire is slowing down at a constant rate. So if the angular acceleration is constant, then it's the same all the time. So the instantaneous value is the same as the average. So we don't have to write the bar over the alpha. Okay, so for constant angular acceleration, all right, just like in chapter 2, constant angular acceleration, the acceleration was time rate of change of velocity. Here, for constant acceleration, the angular acceleration is the time rate of change of angular velocity. So as an example, let's say I have a wheel spinning. Okay, so it spins at 3 revolutions per second, and then something causes the spin rate to increase to 4. In the next chapter, we'll see that that's a torque, right? You apply a force, the car accelerates. You're going to apply a torque, a twisting force, and that's going to cause the spin rate to change. Now, while we're here, back in the circular motion chapter, we had problems where they gave you a rotation of let's say 3 revolutions per minute or 3 revolutions per second, and we said, what is that quantity? Okay, we said that 3 revolutions per second, we called that a speed. Okay, we called it speed v, but we said it's not in the correct unit. So back in earlier chapter, okay, when we did circular motion, we said, well, we really have to say that in 1 revolution is 2 pi r meters. So that changed it to meters per second. Okay, that went from revolutions per second to distance per time. And then back in the circular motion chapter, we said that this quantity, eventually we'll call it an angular speed. So this is omega. Okay, so omega initial is 3, omega final is 4. Okay, but it's not in the correct units. So when we want to find the angular acceleration, okay, using our basic expression here, okay, change in angular velocity with respect to time, omega final minus omega initial, that omega final is not in the correct unit. It has to be in radians per second. So I did omega final minus omega initial divided by the time over which the change occurred. I had to convert the revolutions. So I said 1 revolution is 2 pi radians. So I'm left with this number in radians per second squared. Okay, now, since A in chapter 2, we treated as a vector, okay, we're going to look at the direction of the angular acceleration alpha. Okay, so here I have a wheel spinning, okay, and to find the direction of the angular acceleration alpha, we use the right-hand rule. Okay, so here I have a wheel, okay, it's spinning faster, all right, so using the right-hand rule, you grip this, there's your thumb, your fingers would curl around the wheel in that direction, thumb points in the direction of omega. Okay, so we did that previously, okay? Or think of this as a light bulb, okay? If you were, and the light bulb was in a socket, if you were twisting the light bulb in that direction, you'd be unscrewing the light bulb, okay? Because most light bulbs are right-handed threaded. You'd be unscrewing the light bulb, the light bulb would move upward, okay? Okay, so here's our spinning object. Right-hand rule says the angular velocity points up, okay? And let's say it's spinning faster. So omega is increasing, all right? Well, if I write the angular acceleration like this, alpha, angular acceleration, points in the same direction as d omega. That's a vector equation, okay? Remember, dt, all right, that's just a scalar, all right? Obviously, time goes forward, so dt is a positive quantity. So whatever the value of, I should say the plus or minus sign of d omega is, that's the same as the angular acceleration. So if omega is increasing, d omega is positive. Okay, so if d omega is positive, that means the angular acceleration is positive. They point in the same direction. Okay, over here, I have the same wheel rotating in the same direction, okay, but now it's slowing down, spinning slower. Okay, so the angular velocity omega is decreasing. Okay, so d omega in that case, okay, this quantity d omega is getting smaller. So that's a decrease. It's negative. So d omega is negative. And if d omega is negative, that means the angular acceleration is negative because dt is a positive quantity. So that means that alpha, okay, is in the negative direction. It points opposite of omega. Okay, so omega points upward. Okay, omega vector points upward. Okay, I'm not going to draw this, okay, but the vector d omega would point down. Okay, I don't need that. All right, so d omega is negative, which makes alpha negative, and that's why alpha points downward. Okay, so this whole treatment reminds you what we did in chapter 2. So in chapter 2, we had a car. Maybe the car is going south to north. Okay, here's the car. You're looking at it from the top. And we said if the car was headed upward, velocity points in that direction. That's velocity. Okay, and their foot's on the gas pedal, the velocity is increasing, then the acceleration points in the direction of the velocity. Okay, so regardless of a coordinate system, so I don't have any pluses and minuses anywhere up here. So if V and A point in the same direction, car's guaranteed to be going faster. Okay, same thing here. This thing is spinning and it's going faster, its spin rate is increasing, so omega and alpha point in the same direction. Or angular velocity and angular velocity and angular acceleration point in the same direction. This case here, okay, the wheel's spinning in the same direction, but it's slowing down. Okay, so this reminds you of a car moving in this direction, okay, toward the north. Okay, but the car's braking; it's putting on its brakes, so velocity is decreasing. Okay, so we said that if the velocity is decreasing, the acceleration points in the opposite direction. All right, and that's the same thing that's happening here. Okay, omega points up, but the spin rate is decreasing, so the angular acceleration has to point down. So even though there's no pluses and minuses in this analysis here, okay, this agrees with what we had in the earlier chapter. Whenever omega and alpha, or the velocity and the acceleration, whether chapter 2, velocity and acceleration, or the new chapter, angular velocity, angular acceleration, whether if they point in the opposite direction, then the object is guaranteed to be slowing down. Here it's the spin rate that's slowing down. Okay, so that agrees with what we had earlier. Okay, now another thing that's new that pops up in this chapter is the concept of a tangential acceleration. All right. Okay, so here I have a spinning wheel. Okay, and I have a bug. Okay, that's a bug. Okay, on the rim of the wheel, and the wheel's spinning. All right. Now, if I ask for what's the direction of the angular velocity, okay, you would use your right hand. Okay, your fingers would curl in that direction. Those would be your fingers, and your thumb would be pointing out. Okay, so the angular velocity of this wheel points out. Okay, right hand rule. Right? Or if that was a light bulb, okay, and you're twisting this light bulb, it would come out of the page. Okay, so we don't need that right now. Okay, so this thing is rotating, all right, and the spin rate is increasing, so omega is increasing. Okay, omega is increasing, all right, and if I look at what's happening to the bug, so at this instant, okay, so the bug's going around in a circle. Click. So right here I take a picture of what the bug is doing. Velocity is to the right, okay, but the bug is speeding up. Okay, it's like a car with a speedometer. So the bug moving right here looks just like the car in chapter 2. Chapter 2, here's the car moving down the street, okay. Velocity is increasing because the foot was on the gas pedal. So velocity is to the right, acceleration is to the right. So take the road in chapter 2, take this road, and now bend it like this, okay? So the car here looks like exactly what the bug does right here. So as this bug is going around in a circle, click. If I take a snapshot of this bug, velocity is headed to the right, looks just like the car's velocity headed to the right. So if I just look at the bug right there, I can't tell whether this bug is a snapshot of the car moving to the right, or if this bug is a snapshot of an object moving in a circle. So just as the car's acceleration is to the right because the speed of the car is increasing, the acceleration of the bug is to the right because the speed of the bug is increasing, the spin rate's increasing. So this acceleration here, okay, is tangent to the circle. Okay, there's a radius, so tangent to the circle. So it's called a tangential acceleration. So that subscript T stands for tangential, okay? So the tangential acceleration is the time rate of change of that. And this thing is the speed. So the tangential acceleration is the time rate of change of the linear speed v. So d speed dt, okay? So in this case, the speed is increasing. I take a snapshot, so the acceleration points in the same direction as the velocity. That's why it's called a tangential acceleration. Okay. Over here, I have the same wheel rotating the same direction, but now the spin rate's decreasing. So the bug's going around in a circle. And if I take a snapshot of the bug at that point, okay, it's headed to the right, so velocity points to the right, but the bug that had a little speedometer on it is slowing down, so the speed is decreasing. So the bug at that point looks exactly like the car from chapter 2. Car's headed to the right, okay, velocity to the right, but it's putting on the brakes. So the speed is decreasing, so the acceleration points backwards. So if I take this road and I bend the road in a circle, the car looks exactly like the bug does at that instant. So that's why this acceleration, okay, there's my radius, okay, is referred to as a tangential acceleration. We didn't call it tangential here because everything's moving in a straight line. okay? But here, the bug's moving in a circle, so the velocity points to the right, but since the velocity is decreasing, the acceleration points backwards, and it's tangent to the radius, or tangent to the circle. So in that case, the tangential acceleration would point backwards. So that quantity, the speed that, okay, so that's the magnitude of the velocity, my absolute value, magnitude of velocity. So this thing I have circled, the speed is decreasing. So the d speed is negative. So that's why the tangential acceleration points the opposite direction of the velocity. Okay, so to relate the tangential acceleration to our angular quantities, tangential acceleration is time rate of change of that, okay? That's the magnitude of the velocity, called the speed. And we know from earlier that v, linear speed, is r omega. So for v, I put in r omega. Radius is constant, comes outside. So I'm doing d omega dt. And we know d omega dt is alpha. So the tangential acceleration, okay, this kind of reminds you when we did v is r omega, the linear quantity v was related to its angular counterpart, v of the radius. Here, the linear tangential acceleration is related to its rotational counterpart, angular acceleration via the radius. Okay, so as this thing goes around, okay, as I go to different points further out from the radius, okay, or from further out from the center of the circle, the farther you're out, the larger that r gets, the larger the tangential acceleration would get. Okay. Now, what about the units of the tangential acceleration? Well, it better be the same units as it was in chapter 2. It should be meters per second squared. So we look at r alpha. So r has units of meters. Alpha has units of radians per second squared. Okay. So remember, the radian is a dimensionless quantity. Okay. It doesn't need to be here, so you're left with meters per second squared. Okay. So that's a new quantity. The concept of a tangential acceleration, and I use this picture to relate it to chapter 2. Now, the bug's still moving in a circle. Okay, that's from our circular motion chapter. So it has a centripetal acceleration toward the center. Okay, so it has a centripetal acceleration. All right, that's the v squared over r. But now in this chapter, they call it a radial acceleration. Okay, so instead of using the subscript c for centripetal, they use the subscript r for radial. And remember, centripetal means toward the center. Radial means along the radius. Now, along the radius could be outward or inward. Okay, so that's not really descriptive enough. Centripetal is a better descriptor. But the reason that they switched to radial is because this thing's going around a circle, and in trig class you did polar coordinates. And instead of x and y, they used r, and theta. That was r and that was theta. Okay, so we use I hat and j hat for x and y, and in polar coordinates, eventually you'll see that the basis vectors or the unit vectors are r hat and theta hat. Okay, so that's why we're going to be using the subscript r, because it refers to the r coordinate for polar coordinates. Okay, so the radial acceleration, right, that was our centripetal, v squared over r. V is r omega. Okay, so on the top I have an r squared, I have an r on the bottom, one of the r's cancel. So that gives me our radial acceleration, okay, which we earlier called the centripetal acceleration. So again, so the linear acceleration is related to an angular quantity via the radius. All right, and you can check, it'll have units of meters per second squared. So the radial acceleration, r is in meters, omega is in radians per second, but it's squared. Okay, so the radian is a dimensionless quantity, and you would have left with meters per second squared. Okay, so that's our radial acceleration, and that's our tangential acceleration. So the thing that's really different in this chapter is that the book uses the word acceleration. If they ask you to find the acceleration, they're asking for the letter A, but A is a vector. Okay, so if they're asking you to find the acceleration, they want that. But the acceleration now, we have two of them. We have a radial and we have a tangential. So in this above, in the example above, okay, there's my bug, okay, same example, here's the bug, okay, and this was spinning faster, all right. So if they ask you to find the acceleration, okay, there's two linear acceleration. You have the radial, whoops, you have the radial, that's from the earlier chapter, that's the centripetal, okay, toward the center, whoops, okay, and you have the tangential because the spin rate is increasing, okay. So remember we had the tangential which points to the right, okay. So now the acceleration is the vector sum. So if I add the radial plus the tangential, I'm doing tail to tail, so making a parallelogram, okay. That arrow, that's the direction of the acceleration. So it just points in some bizarre direction, okay. All right, now, do you remember this shape, right? Was that like a 2S2, 1P3 orbital, or is that an S2, 1 or 1P3, okay? Well, the good thing is that's not an orbital, it's a fan, okay? So that's a fan that's gonna rotate. Okay, so let's say I have a fan, okay? Let's say the fan is on, okay, it's rotating in this direction, all right? And let's say it's switched off and it's slowing down, it's coming to rest, right? While it's slowing down, in which quadrant is the acceleration of the tip of the blade at point Q? So here's point Q, okay? I wanna know what's the direction of the acceleration, okay? And acceleration is A with an arrow. Okay, so by quadrant, remember from math class, that's X and Y. That's your first, second, third, and fourth quadrant, okay? What direction does the acceleration point, all right? So in the homework problems, if they ask you for acceleration, they mean the letter A, okay? So there's two accelerations. You have a radial, because it's moving in a circle, and you have a tangential only if the rotation rate is changing. In this case, we do, okay? So the radial, okay, that's just the same as the centripetal, okay, means the same, it's toward the center. So I drew that one here, okay, toward the center. The tangential, okay, that's the rate of change of the linear speed. So this thing is the fan tip blade, okay, for all practical purposes, we'll say it's going clockwise. So this instant, it's right there at Q. So this instant, it's headed upward in that direction, right? That's the direction of the velocity at that instant, or its tangential velocity, okay? But if the fan blade is slowing down, this would be just like the car headed north, but putting on the brake, acceleration would be down. Here, the tip of the fan blade is headed tangentially upward, but since it's slowing down, it has a tangential acceleration that points down. That's the purple one, okay? So you have two accelerations. You have the radial one that points inward, and I have the tangential one that points down. So I had to add these up, whoops, I had to add these up as a vector. So I have my radial, okay, and if I want, I could put the tangential one here, okay. Here I just did tail to tail. So I put the tail of the radial to the tail of the tangential. I made a parallelogram, okay, just the body diagonal. So that's the direction of my acceleration, okay. So what quadrant is that in? That's in the fourth quadrant, all right. So I just tried to make the analogy for this tip, okay. I drew a better picture. Here, this is like the tip of the fan blade. There's the tip Q, okay. Looks just like the car headed up. Fan blade is going slower. Looks like the car is putting on its brakes, so acceleration would point downward. So you just have to be really careful in this chapter. They ask you to find the acceleration. They mean that thing. And now there's two accelerations. There's the inward one due to moving in a circle, and the tangential one if the spin rate is changing.
Is that the old Mike Brown? Yep. They used to have more damn trouble.